So today we're going to start chapter 10. We're going to cover section 1 today. This lesson has a lot of vocabulary. So my advice to you is come up with some way to organize yourself with all of this information about circles, whether you make a study guide, but keep track of all the vocabulary. Maybe draw pictures along with it as you encounter each one of the terms. So today we're going to talk about lines and segments that are going to be intersecting circles. So first thing we're going to do is define what a circle is. And a circle is the set of all points in a plane that are equidistant from a given point in that plane. And that given point is called the center. When you name a circle, you will use that center point. So for example, if I draw a circle down here at the bottom, and if I added in a point in the center, and let's say I call this point M, I could name this circle that I just drew Circle M. You either need to write out the word circle, or just like with triangles, you could also draw a little picture of a circle with the center point drawn in there, and then put the capital letter, which is the point, which is the center. That's how you name a circle. The definition of a radius is the segment whose endpoints are the center and any point on the circle. The plural for the word radius is radii. So I could draw a bunch of radii in here. Again, it's going to go from the center to any point on the side of the circle. So this would be a radius. I could draw another radii this way. It's got a bunch. So I can draw a lot of radii in here. And again, they're all going to be the same length. So for example, if I told you this purple radius had a length of 3, then the blue one would also equal 3. And so would the black one here. So it doesn't matter where you draw your radii, it's going to be the same distance or equidistant from that center to any point on the side of the circle. And generally, a radius will be indicated with a lowercase letter r. The next set of definitions are for a chord, diameter, secant, and tangent. And a chord is the segment whose endpoints are on a circle. A diameter is a chord that contains the center of a circle. So both of these, the first two, are going to go from edge to edge. What's special about the diameter is it's actually going to go through the center. So let me draw a picture of a chord and a diameter for you. So if I go ahead and draw a chord here, I could draw the chord in purple. It goes from the endpoints are on the circle. So this would just be a chord. But when the chord goes through the center, then it's called a diameter. So the endpoints of these are on the circle itself. A secant and a tangent, these are both lines. Now, we'll also talk about secant and tangent segments, but if it does not have the word segment after the word secant or tangent, know it's referring to a line. So a secant is a line that intersects a circle in 2 points, and then a tangent is a line in the plane of a circle that intersects the circle in exactly 1 point, and that point is called the point of tangency. So for example, for the secant, if I draw another circle here, the secant is going to go and intersect the circle in 2 points. So it's going to like pierce it and go through it. So it would touch the circle here and here. And it doesn't matter where you draw the secant. Again, it's going to have arrows on it indicating that it's a line. Again, the naming conventions that we learned back in chapter 1 are going to apply here. If you do not name the things appropriately with the correct symbol on top of the capital letters, you're going to lose points on the quiz. And I'm going to show you this coming up when we start identifying these parts. And then an example of a tangent and a point of tangency. Again, if I draw another circle here, and the next slide has all of this drawn as well. And a tangent line skims the side of the circle. And it would only touch the circle in one point. And that one point is called the point of tangency. Okay, so here is a larger circle with all of these things drawn in the circle as well as them labeled. So again, remember the chord has its endpoints on the edges of the circle or the sides of the circle. The diameter will go through the center of the circle. And again, it's a segment with its endpoints on the circle. A secant and a tangent are lines unless they specify it's a segment. And notice the arrows. The secant touches the circle in 2 different points. And then the tangent will touch the circle at only 1 point, and that 1 point is called the point of tangency. So the secant and the tangent will go out of the circle. So it says point O is the center of the circle, and it wants us to name each figure. So, and notice the pictures on top of the letters here. This is going to indicate if it's a segment or if it's a line. So OM, let me go ahead and find that in my picture. OM goes from the center to the edge of the circle, making this a radius. MN is also a segment, and it's going to go from here to here, from the endpoints are on the circle, making this a chord. MN, now if I added arrows and it went outside of the circle, so if I went ahead and extended this, then it's touching the circle in 2 points, and it's going out of the circle, making this a secant. Remember, a line extends forever in both directions. MQ, this is going through the center. Let's get a different color here. So MQ is right here. And it goes through the center, which was O. And it goes from edge to edge of the circle, making this a diameter. Now, on the quiz or the test, if your answer was chord, technically it would be correct. But the better name here would be diameter. So technically this is also a chord. That would also be a correct answer. ML, let's get a different color here. ML, and again, notice the picture on top. It's a segment, and this is touching the circle at 1 point. So this would be the example of the tangent segment because that's what's identified on top of the capital letters. If you would just tell me that this is a tangent, you would get it wrong because by definition, a tangent is a line. So when there's a picture of a segment on top of the 2 points, you need to name it as a tangent segment. Now the next one has the picture of the line, so this one would just be tangent. So know the difference.
So if it doesn't have like arrows, it'd be tangent segment?
Correct. And then point M is your point of tangency. It's where that tangent line is touching the circle or intersecting your circle. Now, there's also secant segments, but in this particular case, if I would have said MN, we've already identified MN as a chord. Next, we're going to talk about common internal versus common external tangent lines. Now, to determine if a tangent line is internal or external, what we're going to do is we're going to connect the centers of the two circles. So I'm going to go ahead and add in my centers here. So I'll draw a center in each of the 4 circles. And then I'm going to make a horizontal line connecting those 2 centers. Now, once we draw in the common tangent lines, if the tangent line touches or intersects this yellow line, then it's considered an internal tangent. If it does not intersect the yellow line, then it would be a common external tangent. So right now, this black line that's here is a common tangent. It's a line that is tangent to this little circle and the larger circle. I can also draw another tangent that's in common, and it'll skim along the bottom down here. Both of these are common tangents. To identify if it's internal or external determines if you cross that yellow line. They do not touch the yellow line, so both of the black lines are common external tangents. And then I'm going to draw in here 2 common internal tangents. They can come and skim this way and this way. So the 2 purple are 2 common internal tangents because they cross or intersect that yellow line. So these would be common internal tangents. I've just drawn 4 common tangents to these 2 circles, the 2 external and the 2 internal. I can do the same thing on the next circle. I could draw in the same 2 externals, because it's the same 2 circles. Those are the externals. And then again, just like I did in the other picture, they've drawn the first common internal, and here's the second. Again, remember, a tangent touches the circle in just 1 point. So the purple, again, are the common internal tangents. And then the black lines are the common external tangent lines. I can actually draw a line that's going to touch both of the circles in only 1 point. And because that line does not intersect the blue one that you joined the centers with, this would be an example of a common external tangent because it does not cross or intersect that line that you've drawn in there to connect the 2 centers.
Okay. And how do you know if it's not common? Is it always a common or not?
Well, if the tangent line doesn't touch both circles, so like for example, let's say I drew another circle here. And let's say instead you drew a line here that skimmed along this one, but then went straight through this one. It wouldn't be a tangent to the bottom one, it's only a tangent to the top one. So it's got to be a tangent to both circles. So it's actually a secant for the bottom one.
And are they only going to use one line, or are they going to use multiple lines?
You have to draw the lines yourself.
Right, but how many can you draw with 2 circles?
When there's 2 circles like this, it's only going to have 2 external and 2 internal when they're positioned this way. Okay, so this would be a common external. You could draw another one. Oops, let me draw another black one here. This would be another common external, and then the common internal would cross that blue line or intersect that blue line. So again, a tangent needs to skim and touch both circles to be in common to both. And then same thing here. I could draw another one this way. If the line that gets drawn, just like I did before, let's say it's tangent to this one, but then it goes into the circle on this one. Let's say this is circle P and this is M. This line here, and again, we'd have to add some points here, A, B, C. You could say that line AB is tangent to P, but line AB would be secant to circle P, to circle M. And again, you got to put the picture of it. So that's how it could get the difference. Next vocabulary terms are congruent and concentric circles. So congruent circles are just circles that have congruent radii. They have the same length. They can either be sitting side by side. So for example, you could just draw two circles next to each other. And then label the radius. So let's say I told you that this circle had a radius length of 2. And then if this one had a radius length of 2, then they can be considered congruent circles. So when they have the same radius length, they're congruent. You could also have them overlapping if you wanted to think of them as being like three-dimensional. So like, for example, you could have a circle here. And then let's say the other circle went through it. Something like that, like it sliced through it. As long as they're labeled with the same radius length, let's say this had a radius of 5, and then let's say they labeled this radius slicing through there of 5, they would be considered congruent circles. When you have concentric circles, it's like a bullseye. They're circles that lie in the same plane and have the same center. So we already have a circle in a circle, and again, they're going to share the same center. Let me just draw it around here. So it's like a bullseye. And these would not be congruent because they're going to have different radius lengths. It's slicing through it. These are all going to be circles. I know it's kind of hard for me to draw something three-dimensional, but like if you had something that sliced into it, and as long as it's got the same radius length, it's a congruent circle. Tangent circles are going to be two coplanar circles that are tangent to the same line at the same point. So they're going to be touching. So the first one on the left sort of looks like a snowman. So notice the tangent line is squeezing in between the two circles, and the point of tangency would be right here. And then over here, you could have a circle in a circle, and again, this is the tangent line, and again, it's hitting both circles at the same point. Now, the one on the right, they do not have the same center. So our first theorem, again, don't memorize the number. It's called the tangent line to circle theorem. So tangent line to circle. And what this one states that in a plane, a line is tangent to a circle if and only if the line is perpendicular to a radius of the circle at the point of tangency. So what we're going to be looking for is a little right angle here. And then what we're going to be doing is bringing back our special right triangles, and our Pythagorean theorem, and our Pythagorean triples. Because what I can do is draw the hypotenuse. Here, if BC is tangent to circle A, then that tells me that AB is going to be perpendicular to BC, and I know perpendicular lines form a right angle. And again, what you'll be looking for is to find the length of, say, AB or BC or AC given two of the sides, and you'll be using your Pythagorean theorem. And this is a line, this is a tangent line, and it's hitting at point B, which is the point of tangency. So if BC is tangent to circle A, so it's touching circle A at point B, then I know that this radius, when it connects it, is going to be perpendicular. The next theorem, again, don't memorize the number, memorize the name or what it states. And this one is called the external tangent congruence theorem. So external tangent congruence theorem. So when you have two external tangents, so AB is an external tangent, and so is BC. When they meet at the same common point, they're both meeting at point B, then that tells me that these two tangent segments are congruent. AB would be congruent to BC. Sort of looks like an ice cream cone or a snow cone if you turn it. So as soon as you see that you have two tangent segments that meet at the same common external point, then those two tangent segments are congruent. Now let's just try some examples of everything that we just learned about. So I'm gonna do this in different colors. So I'm gonna use the same figure here for both. So part A, let me go ahead and I'll do this one in red. So they're telling me that OR is 6 and OT is 8. Now, I'm gonna tell you that OT is tangent to circle R. And again, you could also draw a picture and then put the center point. So because OT is tangent to circle R, I know that there's a little right angle here. And now to find RT, I can either recognize that this is a Pythagorean triple, and RT is going to be 10, or do Pythagorean theorem. So you would do 6 squared plus 8 squared, and then RT, we could say that's our C squared, 36 plus 64, 100, square root, 10 equals C, which was the length of RT. Now for part B, let me do that in a different color. Let me do that in purple. So now this time we're going to get rid of those numbers in red. Brand new problem. So now they're telling me that the measure of OTR, this angle right here, is 45 degrees. And then that would tell me that this other angle up at the top would also be 45 degrees. So now what I'm dealing with is a 45-45, 90 right triangle. So if I just take that out of here now, and they told me that OT has a length of 4, then they want me to find the length of RT. Well, I know if it's a 45, 45, 90, I can memorize that the two legs are congruent. So this leg would also be 4. And since it's the special right triangle, I know that the sides are going to be A root 2. So then all I have to do is put 4 square root 2, and that's the length of RT. Let's say you forgot the relationship of the sides, but you knew it was a right triangle. You could also do Pythagorean theorem here. 4 squared plus 4 squared, 16 plus 16, 32. Break it down, 16 times 2, and it still goes to 4 square root 2 for the length of RT. So again, we're going to be drawing lots of right triangles and finding missing sides by using either special right triangles or Pythagorean theorem. Next, it wants me to name a line that is tangent to circle P, but not circle O. So tangent to P, P is the smaller circle, and I can see that this one right here is a tangent line, but notice it goes into, and it would keep on going because it's a line. So this would be my example that it's tangent to P, but it's actually a secant to O. So this would be BO or OB. It doesn't matter the order. And again, because they ask you to name a tangent, you need to include the picture of the line on top of the letters. If you forget that, you will lose points on the quiz. Now it wants a common external tangent to circle O and circle P. So if I draw in my connecting horizontal line here, connecting the centers, external mean it can't cross that yellow line. So my external tangent would be here. It's tangent to both circles, and it would be CD. And again, you could name it in reverse. You could also call it DC. And again, because they ask you for a tangent, not a tangent segment, you need to include the picture of the line on top of the capital letters. And now they want a common internal, so this one's going to cross that yellow line or intersect that yellow line. And I can do this one in green. So the common internal would be AE. Notice it's tangent to circle O at point A and tangent at point E. So AE would be the example of the common internal tangent, and again, include the picture of the line on top of the letters. Again, you could have also named it as EA. A here, let's see. So the tangent line to circle P is right here. But notice a line continues on. And for a line to be a tangent, it would have to skim the circle. So if it keeps going, it goes into circle O. And that's why it's not tangent to O, but only tangent to P.
So even though there's like a stop mark on the O, you have to assume that it still continues on?
Correct, because a tangent is a line.
Okay, thank you.
All right, let's try the last example. So for here, it says circle M and circle N are tangent at P. PR and SR are tangents to circle N. And circle N has a diameter of 16. PQ is 3. RQ is 12. All right, this is going to get a little busy here. Okay, so for PM, let me draw in what they've given me. So PQ is 3. RQ is 12. They also told me that I have a diameter of 16. So I could draw my diameter here straight across, and that would have a length of 16. Now remember, it doesn't matter where I draw a diameter. So even if I were to draw it this way, so that it goes through the little circle, it's still 16. And this would tell me that this radius here of Pn, which is going to ask me, let's see, does it ask me for a radius? No. So this is actually the radius of this, which is also the diameter of the little one. So this diameter here of the smaller circle is half of the diameter of the larger one, which is 8. And then to find PM, which is actually the radius of the smaller one, divide that 8 by 2, and PM is 4. For MQ, I'm going to use my right triangle here. Since point P is a point of tangency, I know that I have a right angle. And when I draw MQ here, I now can see that it's going to be a triple because this little piece was 4 and this hypotenuse is going to be 5. It's a Pythagorean triple.
PM is half of the radius.
Correct.
How did you know that?
Because if I knew that this right here was the radius of the original big one, and the original big one had a diameter of 16, so this was 8 and 8. Yeah. And then half of that is 4. Then PR, that one's easy to find. All I have to do is add 3 plus 12, and it's 15. To find SR, we learned a theorem called the external tangent congruence theorem. And I know that two tangent lines that meet at the same common external point are congruent. So this one and this one are both 15. And then NS is just a radius. So it's right here. So it's going to be half of the 16. It's 8, so half of the diameter. And then the last one, NR, once I draw that in here, it's a triple. It's 17.